channel today. In today's video, we will explain series parallel arrangement of capacitors. Now, this means that you have network of capacitors in such a way that you cannot say they are completely arranged in series or completely arranged in parallel, but if you look at part of it, you will see that this is parallel combination, such as this one. C2, C3, C4 are connected in parallel. C5, C6 are also connected in parallel. But if you look at this one, you can see C1 is connected in series to this network, again in series to this one. So you have three things in series: this one, this one, this one in series. But when you come to the second network, you will see that this is in parallel, this is in parallel. So this kind of arrangement we call it series parallel arrangement of capacitors. The question is, how do we get the equivalent capacitance of this network? Okay, this is the way out. You first of all treat the capacitors in parallel combination. You get the equivalence of C2, C3, C4, and you place it in place of this one so that you have a single capacitor instead of a network of three. You do the same for these two, C5, C6. You get the equivalent capacitance of the two, and you put it here in place of these three, so that at the end you have three capacitors in series, and then you apply the formula for total capacitance when they are connected in series. For example, if the total capacitance of C2, C3, C4, if we call it C sub t, total capacitance 1, and then if we call the total capacitance of C5, C6 as C sub t 2, then at the end we can draw this. You see, between point A and B, we have C1, and we have another capacitor here, which is CT1, the equivalence of this. This means the effect of C2, C3, C4 combined together will be the same as the effect of a single capacitor here, which is the equivalence of the three capacitors there. Now, this one too, you have C5, C6, their equivalence is CT sub 2, C sub T2. So now you can see that they are arranged in series. You can apply the formula for calculating capacitance in series and get the total capacitance here. Okay, let's see one example on that. Problem 1. Problem 1 says determine the effective capacitance of the network of capacitors shown in the diagram below. In this diagram, you see, this is your C1, this is your C1, this is your C2, this is your C3, this is your C4, this is C5, and this is C6. How do we get the total capacitance? So we are going to ignore this C1 first and get the equivalence of C2, C3, C4, and we are going to call that C sub T1, and the equivalence of C5, C6, we are going to call it C sub T2. Great. Now we start with this one, and solution. Okay, we will now say, since, look at this, look at C2, C3, C4 are connected in series. The formula for calculating total capacitance in series, C sub T1, is equal to the C2 plus C3 plus C4, because they are connected in parallel. So we just add them. C1, look at it here. Let me bring it closer. You see C1, 1, this is 2, this is 3. So we are going to say 1 plus 2 plus 3, and this will give us 6 microfarad. Then we take the other network, this one, C5 and C6. They are also in series, in parallel. C5 2 and C6 1 microfarad. So we are going to say C sub T2 equals C5 plus C6, and this is equal to 2 plus 1, this is equal to 3 microfarad. So at the end we will draw it again. We will draw the network of capacitors as this. Well, the first one, remember your C1 is 5 microfarad, and then the total of C2, C3, C4 is this. So it means if we have one capacitor, if we remove all these 3 capacitors and we connect one capacitor with a value of capacitance 6 microfarad, it will produce the same effect as the effect of these 3 capacitors with 1 microfarad, 2 microfarad, and 3 microfarad capacitance. Next, again we have 2 here and 1 here. Their combined effect is 3 microfarad. So we write here, oh, I'm sorry, this should be B, this is A, and then this is 3 microfarad. Okay, now we have only 3 capacitors, and the connection is clearly in series. So we find their resultant. We say 1 upon C, this is now our total, is equal to 1 upon 5 plus 1 upon 6 plus 1 upon 3. Okay, what is the LCM of 5, 6, and 3? Is 30. So you say 30. 30 divided by 5 will be 6, and that 6 times 1 is 6, plus 30 divided by 6 is 5, and 5 times 1 is 5, plus 30 divided by 3 is 10. 10 times 1 is 10. Moving on, we said this is equal to 5 plus 1 plus 10, this 5 plus 6 plus 5, 11, 11 plus 10, 21. So we have 21 divided by 30. Now, what is the highest common factor between 21 and 30? Meaning which number, what is the greatest number that can enter 21 and 30 without any remainder? That number is 3. 3 into 21, 7. 3 into 30, 10. So we have 7 upon 10. But this is not your result, because remember here is 1 upon C sub t. So you take the reciprocal of both sides. This becomes C sub t divided by 1 on the left hand side. On the right hand side you have 10 divided by 7. You turn this upside down. C sub t divided by 1 is C sub t, and this remains 10 upon 7 in microfarad. Okay, for those of you who have problems with obtaining LCM, you can solve it this way. Look at it. You can say 1 upon C sub t equals, I'm going to write O, equals 1 upon 5 plus 1 upon 6 plus 1 upon 3. And this is equal to, what do? You multiply the denominators, all of them. 5 times 6 will be 30. 30 times 3 will be 90. Okay. Next, let me bring this calculator here. So you now say 90 divided by 5. So 90 divided by 5, this will give you 18. That 18 times 1 is still 18. Plus 90 divided by 6. So you say 90 divided by 6. This will give you 15. 15 times 1, 15. Plus 90 divided by 3. Press 90 divided by 3 and you will get 30. Now this is equal to, you now add the numerators, 18 plus 15 plus 30, and this will be 63. So you have 63 divided by 90. Okay, now since the numbers are pretty large, okay, what you will do is you start taking small HCF. Can 2 be a common factor? No, because what we have here is 3, so definitely 1 will remain. If we take 3 can enter 6 and this 3 without any remainder. 3 into 6, 2, 3 into this 3, 1, so nothing remains. You get 21. 3 into 9, 3 into 0, 0, so 3 can enter both without any remainder. 3 into this, you have 21. 3 into this, you have 30, so you have 21 divided by 30. Think of another number again that can enter 21 and 30 without any remainder, and that number is 7. 7 into 21, that number is 3. 3 into 21, 7. 3 into 30, 10, and then you get 7 upon 10. Okay, as usual, this is not your result, because what you have here is 1 upon c sub t, not just c sub t. So you take the reciprocal of both sides, and the left hand side becomes c sub t, the right hand side changes to 10 upon 7, and this is in microfarad. You see, this is the total capacitance. It means all this, let me bring this and explain. It means that instead of having all these capacitors, 5 microfarad connected in series to a parallel combination of 1 microfarad capacitor, 2 microfarad capacitor, 3 microfarad capacitor, and then connected in series to another network of capacitors where you have 2 microfarad and 1 how many of them? There are 6. You can remove all of them, and between this A and B, you can place only one capacitor with this value, 10 upon 7 microfarad between A and B. Just this one will produce the same effect in the circuit as the combined effect of all these 6 capacitors combined together. Okay, alhamdulillah, this is the end of today's video. If you have any question, let me see that in the comment section.